I've got energy going up here, and I've got the energy when they're far apart, and then I've got the energy when they're close together. And so I'm going to make some graph as a function of the distance between them. And we know what this looks like.
What orbitals do the electrons sit in then? They can't be in a 1s anymore because I'm not a hydrogen atom anymore. And so now I need to make a new drawing for my orbitals. And so I'm going to switch over here. I'm going to make the same drawing here that I had before. And I'm going to think about, here's my energy for my 1s orbital. It's here. And here's my energy for my 1s orbital here. And then I'm going to look at that energy as a function of distance and see how it changes. And it comes down and it goes up. And so what I see is that the energy of the electrons started out high, and then as the two came together, the energy came down and down and down and was lower. It's the exact same idea, except now I'm thinking about it as the energy of the electron in the molecule. Here, though, I have two orbitals. I've got a 1s and I've got a 1s. So if I think about that, there aren't endless electrons in a hydrogen atom, but there's a place for 4, if I can think about it, right? Because each orbital could have 2 electrons. And so there's room for 4 when they're spread apart. But when I bring them together, the question is, I seem to end up with only one energy level. It's this one down here. And the answer, there's plenty of room in the low energy orbital for both of them. And so they used to sit out here, one in each, and now, when it comes together, they're both in the low energy one. There's another higher energy orbital I don't care about. It's hanging out at higher energy, but there aren't any electrons in it. And these two, again, are going to smoothly change. Far apart, zero energy, and then as I bring them close together, one of them goes down, and another solution goes up. So the one that is lower, I'm going to call bonding. Why? Because it's lower when they're together. So it makes a bond. If you were there, if you were hanging out in the higher energy orbital, lower energy would be separated. And so you would want to break apart. And because lower energy is separated, this one we call antibonding. Over here, they're apart. Here, they're together. And you can see my drawing is already a mess, right? I've got them apart. I've got this one coming down and going up, and this one going up, and so on. And we don't want to draw that all the time. And so instead, we simplify the drawing. And we simplify the drawing by ignoring all distances except super far apart and bonded together. And we make a new drawing. And the new drawing looks like this one over here. Much simpler. In the middle, I put H2. This is together. And what do I get? I get one low and one high. And so I get one antibonding and one bonding. And then on either side, I draw the little hydrogen atoms on their own. These are apart. So I'm standing up here all the time with my arms apart, high energy, arms together, low energy. That's the way the diagram works. The outside, apart, is the hydrogen before they come together. The middle is what they look like when they come together. So what happens? You get new solutions, one of which is lower, and one of which is higher. And it's not like one of them goes high and one of them goes low. These two solutions are combinations of the others. And so this is my old 1s, and this is my old 1s, and these are my new molecular orbitals. That is, they are now not associated with hydrogen atom number 1 or hydrogen atom number 2. They are the orbitals of the hydrogen. When I combined an s and 3 p's, I got 4 sp3 orbitals. So it's just a rearranging of the mathematical functions. 2 functions in, 2 functions out. And so for this case, I've got 2 low energy and 2 high energy. So here's my diagram again. Okay, here's hydrogen A and hydrogen B. This is energy. The other one is higher in energy. The lower one I would call bonding. The other one I would call antibonding. Now, X number of molecular orbitals is the total number of atomic orbitals. Now we run into the problem with the language. How are we going to do this, and how are we going to think about this? We know how many valence electrons there are. Okay, there's one valence electron in this hydrogen, so I put one electron here. There's one valence electron in this hydrogen, so I put one here. And then I take all the electrons that are in the atomic orbitals, and I draw them again in the molecular orbitals. Because remember, the molecule is the same picture where the atoms are close together. So I have to have the electrons both in the atomic orbitals. That shows me what happens when they're far apart. And in the molecular orbital. That shows me what happens when they're close together. So I drew them far apart. There's two. And so close together, there have to be two. And what do I get? I get two at low. Say the molecule is stable. Stable compared to what? Stable compared to the separate atoms. H2 is stable compared to two hydrogen atoms. So in the same vein, I have to know what the next draw will come up the next one. So that's okay. So what are we going to do? Okay, we're going to combine atomic orbitals to get new molecular orbitals. And this says sometimes you get higher energy, sometimes you get lower energy. Half the time it's higher, half the time it's lower. Okay, so each time you combine it, you get two solution orbitals. Okay, so this is real, honest to goodness quantum mechanics. And these come about because we're actually combining waves. So if you add up waves together, it's a very weird idea, okay? The electron is a wave, which means literally it has peaks and valleys and it has a sign. There are two things that can happen when you can add two waves. Either the two peaks line up together and destructive interference, and it gets us to the antibonding case. I have to look and see. I think I've got time, so let's switch over here and I'll show you this as a picture. Maybe it comes up. Getting out of here. There we go. Okay, so if we go to our friend the Orbitron site here that shows the orbitals, remember we could look at 1s or 2s or 2p. Feel free to go here. They have beautiful pictures of the hybrid orbitals as well. But we want to look at these orbitals for molecular hydrogen. So what am I going to do? I now have an orbital that's on this one. I get a nice big wave. Where? In between the two nuclei. So here's nucleus number one, here's nucleus number two, and here's the electrons in the molecule. Where are they? They're all over the whole molecule, spread out. And most importantly, there's some of them in between the two nuclei here. That's our low energy solution. That's our bonding solution. But it could be that the two waves that I have opposite signs. And when I bring them together now, they don't add up at all. Because let's say the blue is positive and yellow and the red is negative. When you bring them together, they actually cancel out in the middle. And so they get smaller and smaller and smaller. And now which ends up with a higher energy. So remember, every time you have an orbital, you have an energy. The one, they constructively add up and you get a lower energy. Here, they don't, you get a higher energy. And we have to stick some little language on that. When they add up, we call it bonding, and we give it a name. This one is head-on, so it's a sigma bond. And when they don't add up, it's the antibonding, and we give it a little star. So we would say this is a sigma star orbital. So I can look at some other choices here. Imagine I have two p orbitals on something. So this can't be H2. This is some of the bonding in N2. So I've got two p orbitals. One of them is going this way. The other one's going this way. This is the nitrogen atom. This is the nitrogen atom. But I've got the signs so that when they come together, what happens? This part adds up. And so I get a nice sigma bond here in between. So when there's constructive interference, and you add the two solutions, you get a new thing which has electrons in between the two atoms. We do the same thing with crazy pi orbitals. You guys can, I would suggest, come and, there we go. Come and mess around with this on the Orbitron site so you can just look at the beautiful, pretty pictures. Here's a p orbital here, here's a p orbital here, and when they come, they overlap, and they make this pi bond. It looks just like the valence bond picture. And that's because we're thinking about the whole molecule, but the whole molecule is a nitrogen and a nitrogen. So it looks like the bond between the two nitrogens. And so what do you get? You get nice constructive interference on the top, constructive interference on the bottom, and you get a pi work. Okay, how are we going to deal with this for what we do with different molecules? The real together. And there are 2 electrons in the helium 1s, and this is A and B, keep them straight. There are 2 electrons in this one too. And I get 2 solutions. One that's lower in energy, that's my sigma bonding. One that's higher in energy, that's my sigma star. So this is my bonding. This is my antibonding. Now, I have the electrons in the atoms. Now I have to say, where are the electrons when I bring the atoms close together and make a molecule? I've got 1, 2, 3, 4 electrons. I got to dump them in there. So where are they going to go? 1, 2 here. Now I'm out of room in the bonding. I have to move up to the next highest orbital. That's up here. And now I have to ask myself a question. Is the molecule lower in energy compared to the atoms? Well, 2 of the electrons are lower in energy, but 2 of the electrons are higher in energy. And net gain is 0. And so I would say, in this particular compound, we don't make any kind of bond. So for a diatomic, I can calculate what I call the bond order. Bond order. It is half of the bonding electrons. There are 2 bonding electrons, minus the number of antibonding electrons. There are 2 antibonding electrons, comes out to be 0. And so we would say He2 not stable. Okay, which is no surprise to you already. You knew helium didn't make a lot of compounds, certainly doesn't make a diatomic molecule. Why? Because here we've used up all of the room for the bonding and we've left this one for the unbonding. So now I'm going to give you guys some practice real quick. That was lots and lots and lots of talking. Good to see you've gotten practice. I want you to think about helium or hydrogen 2 plus. Think about, can you draw the Lewis structure, and then what is the bond order for hydrogen 2 plus? I'll tell you the secret is, of course, everything's the same for my diagram. That is, this is helium 2 plus, and I've got a helium or a hydrogen plus and a hydrogen, 1s, sigma star. So bond order equals what? And then well, we'll just see if you can figure it out here in a second. I'll give you some choices for quicker questions. What do you think? Ooh.
Okay, so I think you guys have had a chance to look at this. I wrote up here that the way that you want to think about all of these problems. Anytime you have a molecular orbital problem, first thing you want to know, put electrons in and figure it out. Okay, so how many valence electrons are in H2 plus? 1. Okay, there's just 1. H2 would have had 2, but you've now ionized it, taken one of the electrons away, and so now it's just 1 valence electron. So in the atomic orbitals, you could put it as like a double bond. Bond order of 3 is like a triple bond. Bond order of 0, no bond, not stable. Bond order of a half, very, very sad, right? It's kind of stable, okay? It's lower in energy than the two things apart. So H2 plus will stay together rather than breaking apart into an H plus and hydrogen. Is it as stable as H2? No. The bond order is a half, right? Okay? Here, the bond order is a half. Here it's 1. Here it's back to a half. So what you see is there's a sweet spot when you fill the bonding orbitals. That's the best case. But then the next choice is unfortunate. If there are more electrons, you have to start throwing them into the antibonding orbitals. Which is why when you get up to like helium-2, it has just as many bonding as antibonding, and so you don't end up with any stability compared to the separated atoms. Okay, now, here's a crazy diagram. Okay? I've given you now the molecular orbitals for nitrogen. Okay, this is N2. Here's the diagram. Here are the atomic orbitals. It doesn't show them all. I'm going to show them. There's 1, 2, 3 p's here, and 1, 2, 3 p orbitals here. So I've got the 2s orbital, and I've got my 2 p's, and the 2s orbital, and my 2 p's. So this is nitrogen, and this is nitrogen, and then in the middle here is N2. And now my question is, can you figure out the goofy little label? Okay, all the orbitals get names. Often they're just 1, 2, 3, 4, 5. In nitrogen, they get special names, sigma, 2p star, and various things. Which is the highest energy electrons are in which molecular orbital? So
2p star, right? Wait, that would be. I like that answer.
So you actually
okay, let me just stop here a moment and think about this. Okay, we got a couple minutes. Just stick some answer. Put something there. So is there somebody, let's start with, say, we have to look at the answer here. Okay, so this is pi 2p. So can anybody tell me why they picked E? Or did anybody pick E and didn't just click a button? Anybody really convinced?
Because you can see the bonds up there, and double bonds are stronger than single bonds. And it has the stars, and they make it stronger.
Okay, so you said the double bonds are stronger than the single bonds, and then you've gone with this is going to give you some added strength in your nitrogen. It's a very, very strongly bonded molecule. Okay, what about D? Anybody for D? Very popular answer, 93 people. Did we all just randomly press the button for D? It's true. D was somehow very closest to your thumb. And so that's what you picked. How about C? C is an incredibly popular answer. There must be someone who picked C for some reason.
Yeah, why did you pick C?
Because you're going to fill up the lowest energy sections that you can, so.
How did you decide how to fill anything?
Right, so I started with the 2S section.
Okay.
2 are going to go to the bottom, or 2 are going to go to lower energy, 2 are going to go to the higher energy.
Okay.
And then you go up to the 2P, and then they're going to fill up the lowest energy first, so you're going to have 4 in the high 2P, and then your last 2 are going to go into
2 from this nitrogen and 2 from this nitrogen, and then you just filled them up in the diagram. And how many 2Ps did you have for nitrogen? 6. Okay, so you started out with how many total?
Starting at the bottom, moving to the top, where do you end up as the highest energy electron?
Okay, let's work to get an answer here. Everybody. Okay, 5, 4, 3, 2. If you can't answer it, I told you it's C. Okay, 5, 4, 3, 2, 1 here. It's just still remarkable. Okay. What did we think? We pretty much, I drove everyone to C, with the C is the correct answer comment. How are you going to do it? Just like was explained. You can either think about it from the atomic orbitals and then put them in, or just add up. I get 10 valence electrons, so 1, 2, P. Okay, alternatively, I would have known there were 2 here and 2 here, and I would have put those in these guys. There's 4, and I've got P's. I've got 6 P's, and I would put them in here, 1, 2, 3, 4, 5, 6. It's the same idea. So what you want, number of valence electrons, and then fill in. Lowest energy place first, working up. Just like the Aufbau principle for an atom. Where do you put them first? 1s. Where do they go next? 2s. Where do they go after that? 2p. Here, where do they go first? Sigma, then sigma star, then it goes into pi. Question here is, what is the order? And thankfully for diatomics, the order tends to be almost always the same. And so it turns out, if I look at row 2 diatomics, I can do it here. Oh, I'm trying to make it a little bit bigger so we can see. Okay, here's row 2 diatomics. It turns out the order we just looked at is almost exactly the same for all of them. Sigma, sigma star, then 2 pi's, then a sigma, then 2 pi stars, and then a sigma star. Turns out after nitrogen, these guys switch places, but it doesn't actually matter because they're already filled. So as we fill up, what happens? How many valence electrons are there in B2? There are 6, 3 from each boron. 1, 2, 3, 4, 5, 6. And there you go, and you filled up the diagram. How many are there for carbon? There's 8. 2, 4, 6, 8. You filled up the diagram. Nitrogen, 10, just like this. Oxygen. Oxygen, unlike nitrogen, it's got 2 more electrons. Now we've got to put them up in these antibonding orbitals. And they're unpaired. Oh my goodness. Unpaired electrons. Who would have ever guessed? only the people who've done the experiment to see that O2 was paramagnetic. And so it turns out they're unpaired in O2. And then fluorine, we get 2 more, we stick them in. If we now start calculating whether they're paramagnetic or diamagnetic, you can see now this one ends up paramagnetic. Why? It's got these unpaired electrons here.
Diamagnetic, diamagnetic, and then oxygen paramagnetic. I can calculate the bond order. Okay, so if I look at this one, how many bonding or antibonding? You can add them all up, or you can just work your way up the diagram. 2 bonding, 2 antibonding. Those all cancel, and I'm left with 2 bonding. That gives me a bond order of 1. Go to nitrogen, right? If I want to do this for bond order, it's half the bonding. The bonding is going to be 2, 4, 6, 8, minus the antibonding, which is these 2, and I get 3. Nitrogen has a triple bond. Go to oxygen. What happens? Now you have to start putting in the antibonding orbital. So the bond order goes down to 2. Go to fluorine. You have to put more in the antibonding orbital. Bond order goes down to 1. And so for all of these, we can predict the bond order. And based on that, we would be able to calculate bond strengths and bond lengths. And of course, you see that it works out as we thought, that the strongest bond here, which is N2, is also the shortest bond. The one thing that we haven't done here is we're showing you the results of what is a massive quantum mechanical calculation, okay, which actually calculates this energy as a function of distance and finds the exact distance at which you get the lowest energy. So this is what people upstairs are doing with their computers to calculate molecules, is they move all of the atoms around to try to find the lowest energy structure. And so molecular orbital theory is not something to just fill in diagrams and make predictions. It's actually our big quantum mechanics solution. So what happens? Oh, what are we going to do? Woo. Very quickly, just to make sure we've got it clear. Identify valence orbitals and number of valence electrons. That's the first thing. Then you're just going to fill them in. Fill them in up all the way. Make sure you don't get things mixed up for ions. Positive ion, take a valence electron out. Negative ion, add a valence electron in. And then you'll have a diagram. I'll give it a diagram, okay? And then you can fill them in. And then once you've filled them in, lowest to highest, then you can do things like tell me what the highest orbital is that has an electron in it, or calculate the bond order. Okay, so this will all be in your learning module if you're frantically trying to write this down right now, because I'm gonna move on, because I want to talk about this for something that's not diatomic. Oh, no, we'll give you a little quiz to see if you practice. Okay, here's a diagram. So I'll give you 2 minutes here to think about this. I want you to think about a couple of things. I want you to think about, these are very important language things here. There is the highest occupied, that means it has electrons in it, molecular orbital, and the lowest unoccupied, that has no electrons in it, unoccupied, molecular orbital. And so that is the so-called HOMO level and LUMO level, and you want to be able to figure out what they are for this. I also want you to think about what the bond order is. I also want you to think if it's paramagnetic or diamagnetic. And this species is the Cn minus ion. Okay? Here's the diagram. It's all filled in for you. So it's already all filled in. So quickly amongst yourselves decide what the HOMO is, the LUMO is, the bond order is, diamagnetic, paramagnetic. Shouldn't take you more than a couple of minutes. And I'll just do a clicker question, so just answer something you get at once.
question is just so I had a 2-minute timer. Okay, just click something to get some points. If you would like to feel good, the answer is B to the non-question.
You have 8 that are bonded.
Okay, so it's been 2 minutes. Hopefully you've answered the clicker question. I'm stopping. There is no answer because there wasn't a question, but we'll all get points. So, what is the highest occupied molecular orbital?
Cn minus, okay? So again, normally we're thinking about the whole molecule. Whole molecule is just 2 atoms. And is it paramagnetic or diamagnetic? Diamagnetic, because they're all paired up. Okay, so diamagnetic. Great. Now, this is what we normally don't ever think about. But this is the only thing, any difference between valence bond theory and molecular orbital theory. Because there aren't bonds anymore. There's just orbitals all over the whole molecule. So here's methane. Oh, we lost the very important little something. Oh. Okay, here's methane. Here's the valence electrons in carbon. There's 3 2p's and the 2s, okay? And again, we could say that there's 2 in the 2s. We've sort of hybridized them over here. And there's the 1s's here. And they combine in some way, and they make this whole new set of orbitals. So these are now my bonding MOs. And how do I know they're bonding? Because they're lower in energy than they are in the isolated atoms. But none of them can be associated with a bond. In fact, they're weird. You'd think there are 4 equal bonds. There's 4 CH bonds in the molecule. Why aren't there 4 equal orbitals? Instead, there's 1 that's lower in energy and 3 that's higher in energy. And the answer is there's no more bonds at all. We think about all of the electrons being spread out over the whole molecule. And so now, all of a sudden, we think very differently. And we think in a delocalized way. Electrons are not localized in a bond, but they're spread out over the whole molecule. But I can still say, what's the HOMO and the LUMO? This is the HOMO here, it's the highest occupied, and this one is the LUMO. It's much harder to know what the diagram is, and so once again, we would rely on our friends who have a massive supercomputer to do the calculation for us, and they would spit the diagram out. And then they could tell us what are those energies. And then they could move the atoms around and do the calculation again and tell us what the energies are. And if you do that for lots and lots of molecules, what you discover is that the details are different, but the diagrams almost all look exactly the same. And the diagrams almost all look exactly the same because you just get a bunch of molecular orbitals, molecular orbital 1 and 2 and so on, going up. There almost always is no degeneracy. That is, these levels that have exactly the same energy, it's rare, almost never happens. You have to be super symmetric for that to happen. Methane, O2, benzene. If you're not, everything's the same everywhere in some symmetry, any typical molecule, methanol, ethanol, whatever it happens to be, then you just have levels. There's some that are low and there's some that are high, and you just fill up the electrons, and in they go, and away you go. And eventually you get to one that's filled, and that's the HOMO, and then the next one that's unfilled is the LUMO. And the reason we're interested in the HOMO and the LUMO is that's where all the chemistry occurs. The high energy electrons, those are the ones that are going to do some chemistry. And if I want to put an electron into this molecule from something else, where's it going to go? It's going to have to go into the LUMO. And so these are the two that we're always interested in. If I shine light on the molecule and I want to know where's the electron going to go, it's going to be excited from the HOMO up to the LUMO. That's the smallest energy excitation that I can make. And so this difference here between the HOMO and the LUMO energies is an important energy because that's the lowest amount of excitation I can put in to excite an electron up. Okay, so now let's think about this. Here's some diagrams. Right? Here's a crazy big molecule I looked at. These are pictures of the MOs. Okay, not very easy to interpret. The electrons spread out everywhere, there are big nodes all over the place, the wave is changing sign. Nonetheless, that's the real quantum mechanics. So one thing that you can see is that as we move up in these theories, we get more and more accurate, and we get better, closer to reality. But our physical interpretation is totally disappearing. The Lewis dot structures are awesome. Pen and paper and you do double bond. Yay, right? Okay, so easy to physically interpret. Now you get a molecule spread out everywhere, has these wave functions, the electrons are all over the place, there aren't any bonds anymore, it's just the energy of the electron in some orbital. And so it's not intuitive at all. Nonetheless, it's much closer to predicting things in reality. And we can predict things like the geometry of the molecule, move all the atoms around, find the position that gives the lowest energy solution, and that's the geometry of the molecule. Predict what wavelength of light will it absorb by correctly identifying the HOMO-LUMO gap. And so this is the real sort of quantum mechanics, and this is how the tool is actually used by chemists. Most importantly, it's this idea. You want to know what the geometry is. No one uses VSEPR. Okay, VSEPR is just an idea to get close to the right answer. Really, you want to know the geometry. You don't want to know, is the bond angle kind of 109.5? You want to know exactly what the bond angle is. More than that, you want to know what the distance is between the atoms. The VSEPR is never going to give you a bond distance. It might give you angles, but you can't get lengths and strengths. And that's what you get out of molecular orbital theory. So now looking at this, I have a very quick clicker question, which is of having even or odd numbers of electrons. So try to answer by yourself, and then once you put an answer in and your neighbors put their answer in, you can compare and see if you guys are in agreement or disagreement.
Right, the whole reason they're bonding is because they want to fill their own tents, right? Sorry, like I'm kind of sick, so my head.
Okay, let's work on getting an answer in here by 2 minutes. See what we think.
Right, and so when you come together and you make those bonds and you fill those up tents.
This is really good over here.
It's even. Think of the molecule. Pick a molecule, count the electrons. They're even. If you're going to obey the octet rule, you're going to have to end up with 8 electrons. It's an even number. We have not dealt with any so-called open shell molecules. Open shell molecules are things with uneven numbers. So, quick question now. You guys are packing up. I don't know. I'm going to ask you a question. Oh, goodness, now we're really dark. What do you think? Most molecules are diamagnetic, paramagnetic, evenly split between the two. 1 minute to answer the question. You have 30 seconds to answer this one. Okay, we'll stop it here now. 5, 4, 3, 2, 1. See what we think. Most molecules are diamagnetic. Why? It looks like this. Fill them up. Pair. Oxygen, very weird. Okay? Everything else is diamagnetic. And so, here's our floating frog. Little frog hanging out in the magnet. Why is he floating? He's floating because he is made of molecules. And most molecules are diamagnetic. And so when you take the frog and you dump it in the magnetic field, he is repelled by it. Okay? All molecules are, well, almost everything is diamagnetic.
Simone went a little overboard there because she didn't get like a
Oh,
shoulder.
she got a little extra.